Okay, let's get started. It's a pleasure to have Professor Bagchi today here as a colloquium speaker. And the audience doesn't need, I guess, any special introduction of Professor Bagchi. So without wasting further, let me invite Professor Bagchi to deliver his colloquium lecture. Professor Bagchi, please.
Thank you. I was passing through. Okay, right. So as I was saying, I was passing through, giving some lectures tomorrow and day after at Cultivation. And so Ranjit told me almost at the last minute. So this is the talk which I used to give as some more recent work we have done. This is an old subject. This phase transition. And let me get it a little bit organized. Okay, I can look at it. Okay, so as I said, and the lot more interest has come now because of in this thing for the two reasons. One, the nanomaterials and the synthesis of nano and the understanding. Second is the imaging technique that is coming through, so that you can get the transient structures in real time. You can see the pattern formation. And so these two new developments led people to look at several things. A lot of the developments that in this field you can get that were up to 1970s, you can get in a beautiful review article in those is the phase transition series, volume 6, Kantan and Desai. The A was Roshni Desai, Kantan, and somebody else I'm forgetting. It was edited by Dom and Green, Cyril Dom and Green, a series, and there is a beautiful chapter, same name as my talk essentially, first part, the kinetics of first order phase transitions. And there they talked about spinodal decomposition, nucleation, all the things. So these are fairly well developed area of research, and I'll summarize some of them, some of the results. However, when the new results started coming, which were, you can say, more or less historically 2000 or so, and when they started coming, then people started going back, and you will see most of the references will be from 2004, 5, like that. And they found that we don't fully understand what we thought we understood. We didn't understand that way. We knew kind of qualitatively, but now adding to all these things came the computer simulations. So we have the imaging, spectroscopic imaging. We had the, so much burst in our attempt to understand the synthesis of nanomaterials, which, as you know, behave very differently from bulk. I'm saying synthesis, in a nano you can get something which you don't get in bulk, which has led to, in the pharmaceutical industry, the terminology is vanishing polymorphs. We already knew these things in our zeolite synthesis or titanate, that you get things in a nanomaterials which you don't get in. So what don't get in bulk? So some things which became now more the requirement to understand the microscopic length scale and microscopic time scale of the phenomena of this nucleation. So basically, when you mean by microscopic, I really mean microscopic. That means I see, okay, I'm trying to grow a nucleus, and I want to understand growth of the nucleus in terms of adding of single atoms and molecules. So the stage of the growth of size of the nucleus is something we are now interested. And so this is the gas, liquid, solid phase diagram. So I'll be interested, now these are the coexistence lines. Along the coexistence line, you have the free energy per particle or chemical potential the same. So here, in chemical potential of a molecule in the gas phase, is same as that in the liquid phase. Similarly, along this coexistence line, you have the liquid and crystal, same chemical potential. Now, anybody who have done theory or experiment on these things knows that if I want to nucleate a gas into liquid, then I go here, nothing happens, coexistence. You go a little bit far into the liquid when it becomes metastable. Very close till nothing happens. You have to go somewhat deeper into the supersaturation, increase in pressure, supersaturation, or what we call deeper into metastability, when the liquid forms. So in this region, liquid is considerably more stable free energy wise, or much lower chemical potential than gas, but gas continues to exist. And it's quite a delicate task for an experimentalist to choose the region. And this is a very big issue, for example, in protein crystallization, which I have one slide. I hope I'll be able to remember. This is a vast field, very vast field, huge amount of work that has gone into this area, and I probably won't be able to do justice to all this, but I'll mumble a few things, and I think I'll try to say as simple as possible. Now, liquid to solid, which is also so much interest in nanosynthesis, they are the same story, that you have to go somewhat deeper, but then there is a very interesting issue comes in, which is same here also. If I go too much into deeper, then instead of getting one crystalline phase, I get a polycrystal. Too many nuclei forms, and they grow. So I have to very delicately, and if I am very close to the coexistence, you have to wait infinite time to get a crystal. So this is what, some people are told to be, Dorothy Hodgkins and this, other people are just presumably phenomenal in growing crystals which other people couldn't do. That is, they have some specific insight or gift in choosing the region. So part of my story will then be about this simple diagram. Remember that along these lines, the chemical potential of free energy per particle is the same, and we have to go deeper. And I do have a pen. Okay. All right. So basically, in something which will come again and again is the concept of surface tension. Again, that's a very mundane concept, but a lot of understanding was done before, but we'll see something very, very interesting that I'll be able to tell you today. So, if I have I'm a bit tricky about these pens. So this is my old phase. Now, if I am somewhere here, if this is my gas, and then this will be metastable, then at coexistence, both are the same. Then I go to deeply to metastability, then this is where liquid is more stable than the gas. Or I can call this is liquid, I can call this is crystal. Okay. So basic idea then, to grow something, I have to make the new phase, the phase that is going to appear, more stable. And why it does not grow here, we'll see in a minute, and many of you probably know, because that is where kinetics comes in. Okay. Now, this will be again shown in a minute, that the statements that I have made here is again pedagogical, that first order phase transitions are activated process, I will explain that, to nucleation, and that there are two competing factors. If you try to grow an embryo, if you try to grow a new phase into an old phase, then you have two things. One is you are getting the profit in free energy, which is this you are gaining by transforming a part of the system into more stable, but that is resisted by surface tension. As I said, this is a beautiful thing which understanding came from statistical mechanics. This again very simply measured in experiment, but turned out to be extremely difficult to do theory, and they are fraught with a lot of difficulties and misunderstanding and traps. Okay. Now there is a concept of critical size, that when you go above that, it goes spontaneously. So this is the picture that we always had. The picture of a nucleation as a localized and rare fluctuation underlies a classical nucleation theory which is called CNT and is an adequate model for small supersaturations and many cases. However, there are conditions, it is not valid, and that is condition is very important in an experimental domain. We push it to a limit where things, okay. Again, so my A of homogeneous nucleation, I am not doing heterogeneous nucleation here. To some extent, heterogeneous nucleation can be incorporated into the scheme by some simple extension. But the real interesting part is the homogeneous nucleation. By homogeneous nucleation, I mean that I have no dust particle, nothing, no seed. I have a pure liquid where I am growing a crystal, or I have a pure gas where I am growing a liquid droplet, or magnetization, whatever you can in presence of a magnetic field, because I am talking of first order phase transitions. So I go close to critical point or weakly first order phase transition to tell you a few things. So first stage is the formation of a supersaturated state, just that we show. And then a small embryo grows. Now these are by spontaneous fluctuations, these small nuclei, they grow and melt, but then one of them by sheer fluctuation grows long enough to be a critical nucleus, and then growth and portioning and many other things happen. This is a textbook again. So to few things again. So this is the our pressure volume, and this is the liquid and the decrease in volume. So this is the Maxwell tie line. So this is where at the isotherm, say this isotherm T3, these are chemical potential of the two are the same. However, in this region, it is a metastable. It is in this region that my picture here holds that this guy is more stable, liquid is more stable than the gas. Similarly, in this region, gas is more stable than the liquid, and there is the case where the volume increases as I increase pressure. This is the unstable region. This is the formating region, which is now I have given more common with the phase coexistence diagram, where I plot now the it could be binary mixture also, or in just density. If X is a density, then one component system, binary mixture is a mole fraction. Then this is the one pure phase, and one pure phase here, one pure phase there. So this is the region called the metastable region. These regions where this condition holds, one phase is more stable than the other, but still continues to exist. That means because it gets trapped in the minimum, and it needs a fluctuation to go out, because if you consider whole system, and this is very important concept students should know, if you consider the whole gas going to liquid, or whole liquid going to solid, that's not possible, because that's huge amount of activation energy is required. First order phase transition, you have a bulk free energy barrier, that means that's of the scale of about a number. So you have to form the nuclei inside, and that's the only way it can grow. Now, it is the metastable region where, so we push into the metastable region as I grow more there, this becomes deeper and deeper, then comes this unstable region. People have doing a lot of experiments and theory in the unstable region for quite some time now. So the simple theory, what is called Becker-Doring theory, and this is also called classical nucleation theory, goes by this following term. I said there is a profit and the loss. So this is the profit, which is the volume, R is the size of the nucleus, and this is the free energy difference between the new and the old, and this is gain, so there is a negative sign, and this is the surface tension term, this is surface area. It's a very simple spherical model. Now you can minimize that and find out, and you find that as I increase the R size, then this increases, values of gamma is such that small r this increases, so it goes up, and this is where fluctuation come and disappear, but then it reaches a maximum, and that is called the critical nucleus. It's a very common thing in the or almost ABC of phase transition kinetics. This is the nucleation theory, and this diagram of Becker-Doring, and this is the size of the critical nucleus. You just take the derivative and find these things, and then put that back into it, and you find these beautiful two expressions, which are, that means people should know in back of their envelope kind of things, calculation, but it's very powerful. Surface tension here and delta G here. Now look at this term. This is really beautiful term. 16 pi by 3 gamma cube by delta GV square. This is the energy dimension, this is the energy cube, this is energy square. So now, if delta GV is small, that means I am very close to coexistence line, that means somewhere slightly down here. Okay. Then delta GV is small and delta G star becomes very large and R star becomes very large. So then the critical the activation energy, the energy that you need to go over the critical state diverges. Okay, this is very important that it diverges. As it diverges, you cannot grow the critical nucleus. So this is the things will get a little bit more complicated, but I try to give it. So this for 2 dimension. So what people use, this BD is for Becker-Doring. That rate you take a some kind of atom frequency, we call it kinetic prefactor, into the probability. This is just an exponential Boltzmann distribution. Probability of being in this state. So this is the state which was, these calculations were done in Becker-Doring was done in 1940s, and it was at that time this person who also developed the theory of, he was very famous in nuclear shell theory, and basically same thing of nuclear chain reactions and fusion and these things. Same theory he applied here. He did there also. He's a very famous Russian physicist, Zeldovich. He said, okay, this picture of Becker-Doring is an equilibrium picture. It's just going over there. It doesn't have the following things. It doesn't have molecules from growing droplet, molecules evaporate, and then he put it, and that was, you can see the Russian school, there is a famous thesis there of physical chemist, whatever you call it, Smolkowski, who wrote an equation for these kind of things, and he used that, and then he derived a rate to take into case, this is non-equilibrium effect, that means the dynamics that is taking place at the surface. These are very famous and very well-known things, and how do you do it? Okay, this is something is wrong. N plus A, that going to N plus. So this should be kind of an arrow there. So single particle addition. So clusters that develop by, so as you're moving on the free energy surface, you are adding clusters, and it is becoming bigger. Okay, and then on the other hand, if they evaporate, clusters become small. So cluster undergoing this movement on the free energy surface, and the dynamics is done by single particle addition. Still things are very simple. If you do that, then you have an equilibrium constant, just like the one I wrote down before. You transfer it to number space, then things get a little bit, so what happens now, I'll just give one result from our work, but it will come back to it later. When you are growing in near the coexistence region, then you have this kind of beautiful, this is coming from simulation. You see also in experiment, a beautiful spherical nucleus, just like almost spherical nucleuses. But as you go deeper and deeper, just as a picture changes, A is equal to 1 is where the coexistence. Then you just don't have an equation. By the time you go to A3 or 1.3 or so, still is very big. You have to push it. Supersaturation, this is pressure at the point divided by pressure at coexistence. So as I am making more and more metastable, I am pushing the system more and more into the liquid phase. But the system is still hanging on to a gas phase because of the huge nucleation barrier. Okay. So, but picture, when I increase the pressure, remember ACP minus PC, PC is the coexistence, so I am going away from coexistence, just like the red arrows I draw, then a picture changes very, very markedly. Now, how do Zeldovich will say how it will work? He said, okay, I have a single molecule addition, so the flux, I now calculate the flux. Flux is for a single particle adding, this is the surface area, beta is the rate of impingement, and this is the rate of evaporation. Okay? To have some beautiful things like principle of brittle valence to find out the rate of evaporation, and then you can get what is exactly like and very famous in a Smolkowski equation. This is the one very common we do in barrier crossing dynamics, in chemical kinetics. Kramer's theory, Smolkowski theory, huge amount of theory used in many different areas. So we now get a flux going above the barrier of exactly this one. Now he could now solve it by assuming a steady state expression. Is a beautiful solution. You should do it I'm writing a book on statistical mechanics, but that seems to be, I have two monographs on dynamics. They're easy to write, but writing a textbook on StatMech is altogether different story. Because you have to really make everything correct. And it's extremely difficult, you know. Textbook is just a horrendous thing to write. Okay. However, so I put the thing, so the Zeldovich comes out a factor, and Z is the Zeldovich correction, which is typically 0.01. Because of evaporation, crystals dissolve, and that brings the Becker-Doring theory closer to experiment. Still, it was of 10 to the power 5, 6 orders of magnitude, but we'll come to that. And this is a beautiful thing, which is the Zeldovich factor in terms of free energy. I'm sorry, there would be the second derivative there. I won't have the n there. I have made an approximation. I don't want to go into it. But this is essentially Zeldovich factor. Zeldovich factor. 1 minute. Where do you want to go? Okay, I want to go back. Okay. Essentially takes care of the competition between the curvature. And this is a beautiful effect. If curvature is very steep, then this curvature is like this. The molecule goes there, or the cluster goes to the top and goes over. However, if it is like that, flat, then it has more chance to evaporate and coming back. Okay. So, and what is this thing given by? That is the second derivative of a free energy surface. That's the called curvature of the surface. So, curvature large, rate large, curvature small, rate small. This is the beautiful effect that Zeldovich introduced, and this is same in nuclear fission. Same theory goes to nuclear fission. Okay. That was one thing I want to tell, that you will see the concepts are so universal and sometimes so deep and beautiful. The recent developments, I go back to my starting point, that we are looking into many things much more carefully now, and there are beautiful things that are happening. Okay. So Zeldovich correction takes into account of the dynamic effects. Okay. Now, I go back a little bit, non-classical nucleation theory. So this was what we were in 1949. So, at large what will happen now, that is where we do in many cases, large supercooling. We want to grow the crystal fast, so we go to large supercooling. We cannot go to, we get the polycrystalline situation, but we want to push it. So large supercooling, free energy barrier comes down, size of nucleus becomes small. But however, when the size of the nucleus becomes small, thermodynamics may not be applicable. One more complication comes. This we know from percolation theory. A lot of work went in late 70s and early 80s, that when you go really non-equilibrium situation or near the critical point, clusters are no longer compact. They are not real sphere. I don't have a boundary, a phase boundary between the two. This so concept of surface tension and everything falls in place. Around that time, several beautiful theories were developed. 1950-60, square gradient by Kahn-Hillard, Landau-Ginsburg, and tensile functional theory of phase transition came into being. Those who know these fields, a little bit of that, you would really appreciate it, because this is a beautiful connection that I am making now from theories which are in critical phenomena, and they are coming into this nucleation area. However, people made many mistakes. Amazing number of mistakes, very famous people. Okay. Now, these are the questions. I have already said that. One of the things is spinodal is there or not, and mean field theory, MFT means mean field theory. Okay. Now, some of the controversies and mistakes. Unger and Klein. This is Dr. Klein from Boston University, and Unger, and the guy who did a lot of work. They predict, I told you that I am slowly moving. This is the pre-2000, then I'll come to post-2000. Predicts that the critical radius of nucleation diverges. It's very interesting. This is in terms of magnetic field, because these are all phase transitions universal. First order phase transition is in the presence of a magnetic field. HS is the spinodal. So now they are saying, when you go to large supercooling, so I can let me draw one more now. And this is the Maxwell tie line. Okay. Pressure against nucleation spinodal again continued that region, and the limitations of mean field and tensile functional theory. He wrote a paper, but he came to completely wrong conclusion. He said Okay, the square gradient theory GT, that which is essentially Ginzburg-Landau kind of theory, where you expand free energy in density in terms of the coefficients. Those of you who know Landau theory of phase transition is an extended version of that. That is essentially a mean field theory, but it is a little bit more quantitative, almost the same. Both of them, they show numerically, this can be found by Kahn and Hillard for these quantities, holds quantity. Then they also say that the critical size divergence. The divergence of Arster is due to the divergence of the mean field isothermal compressibility that they put into the theory. It became really very, now entered the guy who probably never made a mistake, absolutely fantastic. He said a beautiful analysis in the Journal of Statistical Physics, 1986, Bart Binder said, no divergence of cluster size at this spinodal unless the range of interaction, you push it to mean field limit. Range of interaction becomes infinite, that's the Van der Waals limit. Transition from metastable to unstable is characterized by transition or activated to continuous growth. But that was really, because when we were doing the theory and we are getting completely different results from other people, Binder, when I read Binder, that was really quite a okay. There's one guy who is another extremely smart. And now I have come to 2000, right? He pointed out, look, all these classical theories could be wrong because surface tension decreases approximately linearly. Now this is a very important result of critical phenomena, that when you approach, you go to higher and higher temperature, the gas and liquid, here the critical point, they have the same density. So they approach each other. As they approach each other, surface tension decreases because critical phenomena says the surface tension goes as an exponent close to 4. Mean field theory gives 3. Exponent 4. So it is rho L minus rho G to the power 4 surface tension. So I am bringing them close together. The surface tension decreases. It's a beautiful result, actually. So he now says to the right direction, the theory now gives a smaller critical radius as you go to the nucleation. Okay. So there are many other theories and calculations that went on into that. Now, when you did that, the reason we went into it not because of gas liquid or liquid crystal. We are doing a lot of work on liquid crystals then. And I'll tell you a slide or two of liquid crystals. We tried to get the understand formation of nematic liquid crystal from isotopy. So it is isotopic nematic, and I wanted to understand nucleation of that because it turned out to me appeal to me because here I have these molecules which have to line up at the same time. It's a very weakly first order phase transition. The isotopic nematic phase transition, the orientation of phase transition, very weakly first order. And so that gives the unusual, non-classical effects in the nucleation theory. So we wanted to understand that, and we didn't go anywhere. Few papers have come out of this, but I think it's still not a very difficult problem to do. So, as a theoreticians, what do you do most of the time? You do what you can. So we went back to spheres, and we started trying to do a Monte Carlo simulation. However, when you try to do a Monte Carlo simulation, it's a very well-known problem. You cannot treat high barrier. Pore sampling of configurations, near phase transitions, everything. So the way you do it, I'm again going to go very qualitatively, that so when you try to do this simulation, you have your system is stuck here, okay, and there's a large nucleation barrier. So then when you try to do a simulation, your system stays here. It does not go here. So you don't get the rate. But to get the rate, you have to sample configurations here. That could not be done. So now there are sufficient techniques that were available when we started working on that. One is called umbrella sampling. What you do, you put a weight, external weight, outside to the Hamiltonian. And then you force the system over there. Then you can sample that, but you know the weight factor. And this is where a lot of creativity, a lot of innovation comes in. The weight function to be chosen, and you have a freedom in choosing the weight function. And when you do that, you can put it, and then we can take it out. You can take it out, and so this I said I can put a weight factor, and then I do sampling there, and then I can take it out, I correct it, I know. So I get the zeroth order, original distribution that I want by, again, I don't want to go into these details of Markov chain, and several reasons for that. One of them I myself is a little foggy about it now. Okay. Most common choice that was done, it was introduced by these kind of things for the first time is value and Tori in 1979. 1979, value and Tori from University of Toronto. Okay. So one is a harmonic. You want to go to xt. This is the region you want to go. You are in x0 to pull it through a spring, and that is you add this thing. So it goes to that direction. Other is that you weight, W-E-I-G-H-T, weight those which are less powerful. So one way of doing that, minus log, this is called adaptive method. So the guys who are less powerful now getting more weight, because this less than 1 rare, and so it is it becomes plus and becomes, so it pushes the system to, so this is a feedback mechanism. This is called adaptive thing, and it was done by these people. Okay. So I give an example. So Ising model, and start here. If I do Monte Carlo simulation, but doesn't matter. Doesn't matter how long I go with the magnetic field, so that it stays at -1. It just stays there. You can go on eternity. Nothing will happen. You will not get the other phase. Even if you have switched. So you created in a down spin, now you switched it up spin, but system won't go. But now you do with the transition matrix Monte Carlo, you sample the whole thing. You sample the barrier region. So this is a very powerful technique we now used. So mechanism, nucleation and growth near gas liquid spin order. That is my aim. Okay. We did that. We now define what is the liquid. The people have done what is the crystal. You said, okay, gas is here where one guy has 1 or 2 neighbors. I call a particle a liquid-like particle when there are 10 neighbors. These are our order parameters. These are the, and then I think nothing is there. Okay. So going back a little bit, that as I talked to order parameter, this is nothing but reaction coordinates. Those who are chemists here. So Landau theory, it is the density difference in magnetization, in magnetic systems is magnetization, and then these are kind of coarse-grained order parameters. But now the results are really very interesting. So now free energy surface, which is moderately supersaturated. Remember P by Pc is 1.8. Now free energy barrier is still very large. So I start here, which is low liquid-like. This is the gas, and it has to go over there. Look at the curved character. 2 order parameters and liquid-like clusters. The total number of particles in the system. It's a grand canonical simulation. So more particles come in when there is a system is becoming liquid-like. So it goes from this way. This is free energy like that. But still barrier is very large, and barrier here is about 10 kBt or so. But and now when you go to, here is the 10 kBt. When I go -10, I'm going from gas to liquid, and this is the saddle of the barrier, 2-dimensional potential energy surface. At that time, because the first time it was drawn like that, but you can see the huge barrier. But now when you go to really super near spinodal one can find it's around 2.4, 2.5 in this parameter space that I'm using. Now it has come down. It has come down. The barrier this has become flat, and barrier has come down. And I hope I have contour. Yeah, now the contour diagram. Look at it. Now here is I'm starting gas. It's going to liquid, but now the free energy barrier has really come down. It's just about 2 kBt or so. So it produces now all the things. But there are certain surprises. One surprise is that you find that the whole scenario changes as you go from low supersaturation, and Kahn-Hillard or those kind of spinodal decomposition completely breaks down. And this is the picture I wanted to tell you, that low supersaturation, low metastability, you have this kind of picture. But when you go to large supersaturation, near spinodal, everything, so nuclear grows in a continuous and a collective manner. This is what happens when you get polycrystalline. Many things start growing. all over the system. So there's a collective fluctuations. And I want to show you one more picture, not this one. Yeah. So low supersaturation, low metastability. You see, you have to wait for a long time. It has all different runs, but only in one run, the cluster. This is the cluster size. Cluster starts growing. So this time, this cluster size. This time. So only one. It is growing. You can last for a long time. This is one. So it is okay. You get a one single crystal, but you have to wait for a long time. But when you get a large supersaturation, everybody starts growing. So now your growth is collective, spread over the whole system, and many places your clusters or nuclei starts growing. This is the polycrystalline situation. So now we have a handle on going from one limit to the other limit. So there are more pictures. So this is as far as I go to spinodal and gas liquid. I'll come back to spinodal a little. So please don't hesitate to, because I am going to change a little here, tell you something which is which I regard very interesting and new. Okay, so a lesson from glass transition. If you guys know what is a glass transition, that it is a small region of temperature when I'm cooling. Viscosity becomes very large. Viscosity becomes something, say, from 100 to 10 to the power 13. The very small temperature region. And lots of very important things happen, like specific heat shows an anomaly, some sign compressibility shows an anomaly, but mostly it is the dynamics. So this was supercooled water and then other supercooled liquid, and this work was essentially what I'm going to tell you a little bit by this Virin, and then further developed by these three guys, Himalayan Martinis. So the basic idea is that system breaks up into small patches, and each one relaxes with its own time step. So relaxation is what you call heterogeneous. Each has its own dynamics. Okay, and so this is the called Hartford theory, very famous theory of glass transition, highly controversial and highly debated. People hate it and people also love it. Random first order theory of this transition, glass transition, which essentially says that you have these regions which undergoes, if I am in glass, hitting it, then they becomes liquid at different times, and that gives a heterogeneous dynamics. I am not really going too much into glass transition. As I have said, I want to bring only a lesson from that. The lesson is the following, and it's a beautiful lesson. So I write the same thing I wrote before, right? Just I wrote this one first. So I just surface term first and so on. Only difference is that what I called delta GB before is TSC. SC is the configuration entropy. TSC is the part of configuration entropy to free energy. So delta GB is just entropy, because liquid and the glass have the same, assume in this theory to be the same enthalpy. So they only differ by entropy. So this is TSC. Even that is not my aim here. My aim here is what is in this box. This is a beautiful result came from randomizing model. That said that the surface tension depends on the radius. This is perhaps the most important, and one more I'll see. I'm pointing out the slide of this. This was first obtained by Villain, not Villain, sorry, and randomizing model contest, which was used by Martinis and more extensively by Zia and Martinis. And this comes, and there is a beautiful physics in it. The physics is the following. Physics is that when you have a random system, you say you have a semi-ordered region. Now, next to it, you can have a large possibility of less ordered region, which is called weighting. So I can weight a region by many intermediate phases. So, and you'll see how beautiful the physics is in 5 minutes. But as a result, there's a dramatic expression, analytical. Now I go there and put this back into my theory of nucleation, and lo and behold, I get back what is a very famous Adam-Gibbs relation between relaxation time and configuration entropy, which Gibbs DiMarzio theory, Gibbs was my thesis advisor, Gibbs DiMarzio theory says that last transition where configuration entropy goes to 0, but then later 1965 Adam and Gibbs derived this relation, that which is enormously used, one of the most famous equation of the condensed matter physics. Adam Gibbs is the household name in this. It is essentially, see, there's a great saying, always I quote, I recently wrote a blog and I forgot to talk about my blog because that's my new passion. But there's a very famous saying by Dostoevsky, Fyodor Dostoevsky. The young generation, they don't know about Dostoevsky, but our time we used to be really completely with taken very much by Dostoevsky. Now, there's one writer before Dostoevsky whose name is Gogol, Nikolai Gogol. I don't know whether you guys have read The Namesake by Jhumpa Lahiri. Any of you? One person, good. Read that, that's great. That's why the name was Gogol, was that father gave the name for a reason. Okay, whatever. Dostoevsky said about Gogol one great thing, that all of us grew out of Gogol's overcoat. Gogol wrote a wonderful story, which is overcoat. So, similarly, whole of class science essentially has come out of this beautiful equation which connected a thermodynamic property, configuration entropy, to a relaxation time. This is also not my, I can give a 4 or 5 lectures on class transition, but not, my only aim is this one now. So, if I can have a phase, one phase, weighted by intermediate phases, which is intermediate between A and B. A is my one phase, A is E, this is B. But if I can have many phases which are in between, then surface tension will go to 0 as 1 over root R increases. Okay? There are more things that came out of Wallace and all these things, we don't need to go into it. Okay. Now, one thing you should remember about surface tension, which is really beautiful thing about surface tension, that I can talk of a surface tension between the two phases only when they are in coexistence. So, two phases must have the same chemical potential to talk of a surface tension. They must exist together. Okay. So now I constructed, I want the surface tension between this and that in final, but I say there are many intermediate phases. Now I can do an exact calculation using density function theory. And that we did, and essentially land out this per level, and we got a beautiful relation which I say yes. When I have more intermediate phases, which is n, is the number of intermediate phases, then the surface tension between 1 and n rapidly decreases. And the reason is very simple, and I'll come to that. It's not only simple, it's actually beautiful. Absolutely fantastic. Okay, as I was saying, you will tell a little bit about it. I'll come back to this, just the beautiful thing that is here. Okay, I was talking of the phase transition in liquid crystals. That's where it all started, all this work. And a liquid crystal, we found a wonderful thing. We found that when you try to get, you remove all the vibrational, translational, heat effects. You get a configuration part one. You find that the isotopic phase, nematic phase is never the ground state. It always goes to smectic, if smectic is there. So, a nematic is ephemeral. That's one of the reasons is a weakly first order. And that will play a very important role in a theory of nucleation that we set out to do, but we have not yet been able to do. And there are a lot of very beautiful things. This is order parameter, how it goes to, isotopic goes to nematic. You can look into this paper. There's a very nice paper. It's okay. Let me go back and I'll come back to politics first. These are very, okay. Now there is a very big paper, very big work that is Ostwald phase loop. Okay. There's a very famous, called father of physical chemistry. Okay. So he made this beautiful statement that formation of a phase is not determined by absolute stability but by the closeness of the growing phase to the parent phase. So he said that it's always, it is not the most stable phase that forms. Initially, it is always the phase that is closest to it. So if you are going from silica melt, it will be faugasite that will form. In case faugasite, you don't see faugasite. You get the quartz or calcimite. That doesn't mean faugasite didn't form. He went on to say, if you see a violation, then you have missed the intermediate phase. So I used to have all the quotations of these, and these are all very beautifully connected, surface tension, all these things that I'm going to do, then I'll see what I can do more. Okay, these are experimental results. I think it is lithium ferrous phosphate, and they go through many phases and intermediate crystallization, as I already referred to. Zeolites, you start with silica gel, faugasite, calcimite, and finally go to quartz. What is happening? Now this is a graph I wanted to show you. What is the role of this intermediate phase? There is a hidden role. If, that's what exactly what they say, great Ostwald say, but this is the first time one worked it out, that, and this is already pretty famous work now. What we did, we constructed these free energy surfaces. So this is an equilibrium. So I am now going to calculate surface tension between this and that. And there is a metastable phase. Okay. And this is non-equilibrium situation. Now let me tell you what is surface tension. Surface tension, again I used to have very nice slides, it's not here, but so I have to do it now in orally. So let's see the metastable state is not there. Then this will go up like that and come down like that. Okay? And what is the surface tension? Surface tension means the extra energy that you have to pay to bring these two together. Okay, that's the surface tension. Okay, so why the extra energy? Because when you put two phases together, there is something in between. In between order parameter, and that is in the intermediate structure here. So the whole origin of surface tension, that this one goes up like that and comes down. So this is the region. That's how you can derive a simple expression for surface tension, which was pretty good, just from free energy surface. It's like a Marcus theory of electron transfer that we are very able. But now, if I have a metastable state, then what happens? This intermediate region need not have that much energy. So your surface tension drastically reduces. This is a beautiful thing. As I told you, this is the second most important of this talk. And then one can do, as I tell you, that it's a very detailed dynamical calculations I do. Density functional theory at Landau Ginsburg level, except that we know the quadratic term, fourth order term, we can work with this one here. And then we see, now indeed, weighting, when I increase this, then I go over. If I increase this one or make it more and more stable, then I get weighting. That means this guy gets more and more. Nucleus of SS, stable phase, gets growing in melt, it gets more and more weighted by the metastable state. But if I go above like this, then I get what is the classically expected. Now the fun part of this thing is that this can play a hidden role. So in zeolite and all these things, it plays an enormously hidden role because you really don't get this phase. Okay. But this comes in and plays a very, very important role in your, and there's a lot of story here, as you can see, which I'm not going to go into. So that how free energy barrier, now you can directly calculate without calculating surface tension from density functional theory, what is the free energy barrier. And as this comes down, you can see the free energy barrier comes down quite dramatically. And makes it here. So there are different crossings, and these are the kind of things people found in experiments. Many cases that how one phase, one dominates over the other, and there is a crossover from one to the other, and then you can grow. You can have this kind of scenario. These two are still in the same, has to be in the same thing. Then you can get the weighting. So in nature of weight, and this is known in simulation. For example, it is known if you are trying to grow an FCC, it is weighted by BCC. Okay, and that because BCC is close to liquid, so BCC forms. Then out of BCC, the scenario is that what you find is coated, and this is the kind of thing I am saying. So when SS growing from the melt, now they are non-equilibrium situation. I have to put this and those together to get the surface tension, this and this chemical potential together to get surface tension. And like that, now it will be, my stable will be coated by M2, that will be coated by M1, then will come to melt. And these are the dynamical crossovers. This I saw in several images. I don't have the images because I am in solid state department. So this is a common thing, and there are more detailed dynamical calculations that I don't want to go into it. We did some simulations in a two-dimensional molecular system. Okay, I take 5 minutes. And this is a called Martinis bench model. As you can see, this is just Martinis bench, and there are interactions, very complex interactions, but one can simulate in two dimension. And one find a beautiful phase diagram that you have an oblique phase, honeycomb and liquid, and then you get the free energy. You can do some sophisticated calculation to get the free energy surface under different conditions. But the one I want to show you is this one. So if I start from honeycomb and go to the oblique phase, then there you find the, as the oblique starts flowing, you find the red ones are of the intermediate phase. So when these are two-dimensional, so this kind of nucleus you can see growing, but many things are growing. These are first order, but you can see the weighting, then finally it goes over that. But you see the intermediate phase. So if you look at that, look at this, you won't know that the mechanism is completely different what is predicted by classical nucleation theory. There are all the diverse local structures you get in this beautiful model, which you in a liquid, or here you get the oblique phase, you get the honeycomb, all these things. So just last bit, that spiral decomposition, as I said, that is considered initial state, exponential, these are all connected. Beautiful, beautiful. This is very common in rocks and binary mixtures, alloys, the spiral decomposition, beautiful patterns that they form. So there was this work by Hillard, same kind of work that he did here, and he said an exponential growth. And scaling regime Kawasaki, Suzuki said no, it's a power law. Kawasaki says T to the power 1/3, Suzuki said in the long term it's T. And these are the simulations we did. These are what's still going on. So binary mixtures, red and blue, and when you quench, then you know it is the parent, homogeneous, quench, then the pattern starts forming, and in a long time, not too long actually, but you can play around with that with the parameter space, you get a beautiful, beautiful spinodal comes in, and then we looked at the structure. This thing went back because in Stanford, in Michael Fair's lab, I was a very good friend with a senior Russian scientist, who is now in Princeton. He used to do these experiments, and he was doing the experiments in a beautiful way. He was taking binary mixture liquid binary mixture, not the solid, where we know spiral decomposition, and he was putting a dye there, which was hitting with a laser light and dumping a lot of energy. And this system they chose as a lower consolute point. So they were pushing it into the metastable region and inducing phase separation between the two. And that was the reason that we did the theory. But indeed, there's a lot of fun doing these things. As I said, a lot of new things are coming out because of the new beautiful experiments coming out. So initially is the exponential growth, then goes up in between the T to the power 1/3, then finally linear. So we get Hillard to a Kawasaki, and then get you Suzuki. I'm not going to lot, and I'm skipping the other things. So this what was done to a great extent by nucleation and spinodal decomposition was done by Monte. Actually, it was started by Prof and Suman. Usually I don't talk that detail of the nucleation, but Suman is in NCL, Prof is in Hyderabad IIT, Rakesh is still in Princeton. So Suman and Prof, then Rakesh and Monte, they did the nucleation part. Soika and Rakesh did this oblique, the Martinis bench model. Seki-san did some work on the rugged energy landscape. Several papers have basically, we didn't talk of him. Rajiv worked on the Soika, the air and polydisperse, and Milan Hazra, Somister did this, doing the spinodal did and doing the spinodal decomposition. Milan is still a fourth year student who is also did. These last graphs that I showed are done by Milan and Somister on the spinodal decomposition. So to end, this is really enormously interesting field, huge field of kinetics of phase transition, which is undergoing completely regeneration. It is becoming a completely, as I said, is motivated by the imaging, because we can now see these images, as I already showed you in the postural phase route. These are very new results. That one, before we couldn't see the intermediate phases, now we are seeing the intermediate phases. So we are getting the kinetics, the transient kinetics, and we are also done by these laser experiments of Michael Fair and all these people, that they can internally change the temperature and drive the system to another region, stable region. And then spectroscopic techniques. So because of that, this field is becoming, and when you go back, you start seeing the many limitations of earlier work, and you can have a lot of fun in trying to understand in microscopic. Thank you.
Questions, comments? Please. There is anything that you like? No? You're more hungry.
Yeah, this is a bad time.
Sir, I have one quick clarification and one question. I'm online. So, sir, one thing that by binary liquid studies, you said that energy was dumped on the molecule, and what did they measure? That how the molecule is coming to this equilibrium downstate or something?
No,
What
they
was
see how the
What is R of T here?
They see how this dye molecule is getting surrounded by the other phase. So it is a lower consolute point. The phase diagram is something like that. Here below homogeneous, up is inhomogeneous. So they give the dye, which dissipates energy, temperature goes up, and then it goes to the up. Now the dye, if it gets surrounded by those which are more hydrophobic. So exact experiment they did is 2,6-lutein and water. So it goes to lutein.
So it's a solvation kind of
Yeah,
experiment.
it's solvation, but they see the phase separation through solvation.
So one clarification is that you said that microscopic aspect of dynamics, something like that. So if I change the resolution of the microscope, for example, then dynamics will remain. That is the property of these systems, sir. So
No, what is happening, by that I said the, okay, so this is kind of gives you so earlier days, people use the systems which are very slow. Carl did the alloys. So the time scales were seconds, hours. Look at the Gunton and Desai, I'd say. The time scale is in hours and days. They also saw the breakdown of the exponential regime. Okay. However, it is very difficult in these things to describe, to find the other behavior that, like, this is essentially what we call the Wagner-Lipschitz Oswald ripening, essentially. The Oswald ripening, that this thing here. No growth. Late stage of the growth. Coarsening. This is the coarsening part. Now, when you go to those places, then what happens that you have a lot of important physics comes in, like hydrodynamic interactions. And details of your coming down of the free energy surface. Actually, what Suzuki did, he said, okay, I have this kind of a double OA potential, and I am putting my system on top of that. So, a classical, that I did not do a good job at all, but classical way of talking of spinodal decomposition is, this is the homogeneous state, and this is the space separated state. I suddenly lower the or increase the temperature, so I am a system which is distributed like that, I am putting it into that. Now that undergoing phase separation. That is the process that, so what Suzuki did, he said, okay, it will matter after you come down a little. Then there is an inflection point here. The energy surface changes character. It becomes harmonic coil from this kind of a thing. And this kind of region you have to take into account. So people never thought of these things. So that was Suzuki. And he's a very brilliant physicist from Japan. Then Kawasaki, he said, okay, another thing that is important when they are separating, there is a hydrodynamic flow that will be created. The molecules are moving this way, molecules are moving that way, like this picture. Here, this picture. Molecules are moving in path almost. So these are the things which were classical theories did not do. Very few experiments exist. The experiments they do in huge polymers, and they are not very clean. That's why the Stanford group, Michael Freer's group, was doing this clean experiment, and that motivated us to do this last calculation that I showed you. So it is directly from Stanford.
So, according to the picture that you showed, that the surface tension depends on the intermediate metastable states. So that means, I have to have an idea what a metastable state should be. Otherwise, I cannot interpret the surface tension values, etc., right?
No, what you need to, what is that? Like, take the case of quartz. What you need to have, if this is a land of free energy surface, this thing is land of free energy surface, okay? So, like in, take the FCC liquid argon, or any FCC forming liquid, and then you know there is a BCC.
Yeah, yes.
Remember that the density of FCC is substantially larger than BCC, and that is substantially larger than liquid. To give an idea to students, if one is 0.5, other is 0.6, other is 0.7. BCC is in between liquid and FCC. It is in between. Simulation, you always experience, you always find that FCC is quoted by BCC. There was no explanation of that. This is the first time a really microscopic, semi-microscopic, because density function theories, and with Ginsburg-Landau as certain, but it's a very established and very honored and respectable theoretical scheme that one uses. This came out, as I told you, this is really, where is that? This I really recommend everybody to read. Even with my paper, it's very, yeah, this one. This is really very good. This is Monte and Rakesh. Their first slide. Yes, and this is because I said it came out from Williams model, and that was I learned from Peter Wilkins's work on blast transmission. So it's just fantastic. Yes,
Sir,
you have to shout.
I have one question. How do you distinguish between this ripening, nucleation, aggregation, etc. in terms of dynamics? Say, given some dynamics is given, then how do you identify the process?
Basically, the way you do the experiments in nucleation, gas liquid nucleation, you go to cloud, we do it on cloud chamber. To get it, you supersaturate it, wait for some time, nothing happens, then suddenly you see a burst of, clusters appearing. So, the time determined state, much of the time is nucleation. But we do not see the nucleation, we see the growth. There is a huge amount of ambiguity even now in getting the rate of nucleation. Estimates differ by 10 to the power 10. 10 to the power 10. That because when are you detecting it? We detect only during the growth phase. We don't detect it in the nucleation phase. That's why so much also theoretical work goes into it. In simulation we can see. I don't have those things anymore, but we can really see that cluster is growing. Then you can see the questioning. So to answer your question, we don't see nucleation we can study the rate of nucleation through growth. Say, for example, how much time it took to grow, for example, say 10 nanometer. These days I can do it, but earlier we couldn't do that. I could do only probably centimeter or millimeter. So then I change the conditions, make it more favorable and less favorable to nucleation. Okay. Now that is the between growth, nucleation and rate of nucleation. Aggregation is in the that comes in the growth phase. So this cluster has grown a lot. It's a very good question actually. This cluster has grown a lot. Then there are two processes that comes in. One is austral ripening. I hope you know austral ripening. I'm not going to go into it now. Other is that amalgamation. Okay. So when they become very big and macroscopic system, it is a ripening that seems to be the choice in many systems. So then they don't, but early, just when they go over the barrier, then you see a lot of this aggregation. So that I think in a solid state like the one lithium ferrous phosphate I told you, people have not seen it. They have seen the intermediate phases like in zeolites. But they will soon or probably already have seen. I have seen in talks snapshots of people just like the picture I have shown you. This kind of picture I have seen, and the paper we are writing now, we are going to put that images. I got it from my colleagues in SSU. Many of you have seen these kind of things in images. These are very common. That you are going to say binary clusters or binary alloy, semiconducting clusters. You always see this scenario. Okay. To what extent I can ignore many other microscopic effects, I don't know. Because this is a free energy based description. There are other things there. But this is imaging, so they are looking at the phases and phase separation kinetics. Then I think what I am doing probably is not wrong. But as I told you, it's a huge field and lots of interesting things to be done. But difficult field, very soon you find out. Not easy. Conceptually very rich, but difficult. And I told you, numerical work doesn't take you very far because things very slow. In binary liquid you are lucky because you could get things in microsecond or so, or 200 nanoseconds. But not in alloys, they will take days.
Okay, so no more questions. Please join me.